Welcome to my video lecture based on utilization of electric power. Paper code PE702. Today's topic is based on some numericals of Illumination engineering. This is the last lecture of Illumination engineering, and the module of Illumination engineering will be finished by this lecture. From my next lecture, we will start with another module of utilization of electric power. Bicentennial Magnitude, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chamushi, Institute of Technology and Space Science. Previously, this institute is known as Dr. Sudhir Chamushi Degree Engineering College, and this institute is under JISD. So let us start with our topic, that is Numericals of Illumination engineering. In this topic, we will mainly cover about different numericals related to illumination engineering. We will start from the first topic of illumination engineering. Then we will go beyond to last topic of illumination engineering. And different numericals based on these topics we will cover in this lecture. So let us start with our first numerical, that is this topic. The illumination at a point on a working plane directly below the lamp is to be 100 lumens per meter square. The lamp gives 256 candle power uniformly below the horizontal plane. Determine the height at which the lamp is suspended. Also find the illumination at a point on the working plane 1.2 meters away from the vertical axis of the lamp. So, in the figure, we have considered that the lamp is raised to illumination and it is illuminating the area in this case and in this case. And the angle between these two is 2. And it is mentioned that the working plane directly below the lamp is 100 lumens per meter square. And the lamp gives 256 candle power uniformly below the horizontal plane. So let us start with the luminous intensity of the lamp is 256. This will be candle power. Illumination at a point on a working plane directly below the lamp is 100 lumen per meter square. It is given. That means E equals to 100 lumens per meter square. Now, let the height at which the lamp is suspended be 8 meters. So, definitely E equals to I by 8 square as per the formula. So, the value of E we know 100, I is 256. And 8 square we have to determine, and we have found that the value of h or height is 1.6. So this is 1.6 meters. Not 16, this is 1.6. Illumination on the working table 1.2 meters away from the vertical axis of the lamp. It is given that also find the illumination at the point on the working plane of the table 1.2 meters away from the vertical axis of the lamp. So this is 1.2 meter away point. So now we have to calculate the illumination at this point. So we will using the formula that B equals to I by A square into cos theta. And the values of H we know, I we know, and the value of cos theta is 0.8. From where we can calculate? We know that cos theta equals to base by hypothesis. From here we can calculate the values, that is 1.6 divided by 2. So 0.8. So from there we have calculated the illumination at the point what would say 1.2 meters. So this is our first problem. Now we will go to next problem. Two 220 volt lamps, one of 60 watt and other of 75 watt, are connected in series across a 440 volt supply. Calculate PD across each lamp. Neglecting any variation in resistance, assuming the candle power is proportional to the foot power of the voltage. Calculate the candle power of each lamp under this condition as a percentage of its value under normal operation at 20 volt. So we have two lamps, one is 60 watt, another one is 75 watt, and we are connected in series across 440 volt. But the lamps are 220 volt lamps. They are connected in series to 440 volt. Calculate the PD across each lamp. Neglecting any variation in resistance and assuming that the candle power to be proportional to the fourth power of voltage. We have to assume that the voltage will be proportional to fourth power of the voltage. Candle power is proportional to fourth power of voltage. Let us start with the problem. Resistance of 60 watt 220 volt lamp. That definitely we can calculate it from the equations of power. We know that P equals to V squared by R. So from there we can calculate the resistance value of the lamp. So when it is about 60 watt lamp, the resistance will be V squared, that means 220 squared by 60, that is 806.67 ohm. Next, we will calculate the resistance of 75 watt, and it will be V squared by 30, that is power. So again this value will be 220 squared divided by 75, that is 645.67. Now current flowing through the lamp when connected in series is 440 volts. So these lamps are connected in series as per the problem. So definitely the current will be flowing through the both lamps, and from the law of ohms can calculate this current. Definitely P divided by R. We will get the value of I. So the values of two resistors are put in series. So this is the two resistors R1 plus R2 and the value of current. That means 0.303 ampere current is flowing through the lamps, both lamps. Now the potential difference across 60 watt lamp utility V1 equals to I into R1. Definitely this is the value of I. And R1 we have calculated, so the potential difference is 245 volt for 60 watt lamp, and the potential difference for 75 watt lamp will be again I into R2, that is 0.303 into 645.33, that is 1954 volt. So at normal operating voltage, that is for both lamps, it is 220 volt. And it is given that assuring the candle power to be proportional to the full power of the voltage. So normal voltage is 220, but in this case we are getting the voltage 245 for 60 watt and 195 for 75 watt. So the candle power for 60 watt lamp, it will be V1 by V, where V1 is 245. The voltage actually passing through this potential difference actually to the 60 watt when it is connected with 442 divided by V, which is the actual rating for the lamp, into the whole to the power 4, because as per problem it is 4 power of the voltage, into normal candle power, that is 100%. So the result is 154 of the candle power under normal operating condition at 220 volt. Similarly, we will do for 75 watt lamp, and we will get that the value of 62% of candle power under normal operation or at 20 volt. That means if the wattage is more, that means the resistance is less. And when the amount of resistance is less, then the potential difference across the lamp will be less because it is connected in series. And in that way, we can calculate the candle power for the lamp. This is our problem 2. Now we will go to problem 3. Third problem. A classroom of size 30 meter into 30 meter is to be illuminated with 75 lamps. The lamps are required to be hung 5 meter above the workbench, assuming a space height ratio 0.9 to 1, a utilization factor of 0.5, lamp efficiency of 15 lumens per watt, candle power depreciation of 20%, estimate number, rating and disposition of lamps. Solution. Gross lumens requirement. Definitely the room size, that is 30 into 30, and it has to be illuminated with 75 lux. That means the area, that is 30 into 30, and E is the amount illuminated, that is 75 lux. So it will be A into E, 30 into 30 into 75, divided by utilization factor, that is given 0.5, into DF, that is depreciation of 20%, depreciation factor. So that is our total gross lumen requirement, which we have calculated 168750. Now we will calculate the total wattage. We know that total wattage equals to gross lumens divided by the lamp efficiency, and for this case the lamp efficiency is given 15 lumens per watt. So the total wattage requirement is 11,250 watt. Now the total number of lamps required, assuming wattage rating of each lamp to be 300, and so it will be the number of lamps required is n. It will be 11,250 divided by 300, that is 37.5. It is the number of lamp requirement. Now 6 lamps can be mounted along one side of classroom, giving space side ratio, and 7 lamps can be mounted along the other side of the room, giving the space size ratio of 30 divided by 7 divided by 5. This is 30 by 30 rule, and we have to consider that 3, 4, 5, 6, and in this way 3, 6, 7. That means here we have to take 6 lamps and here 7 lamps. In that way we have combined the lamps in the classroom. So the disposition of lamps are showing here, and as per this we have taken 6 into 7, 42. 6 into 7, that is 42, and as per our estimation it is 37.5, and approximating that value we have taken this dispositions of lamp which is near to this value. If we are considering in this way 6 lamps and in that way also 6, then we are getting 36, and 36 will be not possible because the minimum requirement 37.5. So definitely the next approach is 6 into 7, that is 42. So our lamp disposition will be just like that, and it will be showing in this figure. Okay. That was our problem number 3. Now we will go to problem number 4. Estimate the number and wattage of lamps which would be required to illuminate a workshop space 60 into 15 meters by means of lamps mounted 5 meters above the working plane. The average illumination required is about 100 lux. Coefficient of utilization 0.4. The illuminous efficiency 16 lumens per watt. Assume a space height ratio of unity and the candle power depreciation 20%. So same formula we have used. The gross lumens requirement, that is area to be illuminated, here it is 60 into 50 into average illumination required. Here the average illumination requirement is 100 lux. So it will be 60 into 15 into 100 divided by utilization factor into depreciation factor. So here utilization factor is given 0.4, and again depreciation of 20% is given, so it is 1 minus 0.2, that is we have calculated 281,250. Similar way we will calculate the total wattage, that is the gross lumens requirement divided by luminous efficiency in lumens per watt. So here our luminous efficiency is 16 lumens per watt is given. So we are getting the wattage requirement is 17,578 watts. Now, for a space height ratio unity, only 3 lamps can be mounted along the width of the room, and 12 lamps can be arranged along the length of the room. So, the total lamp requirement is 12 into 3. So, our answer is 36. This is our problem number 4. Next problem. A hall of 30 meters by 15 meters with a ceiling height of 5 meters is to be provided with a general illumination of 120 lumens per meter square. Taking a coefficient of utilization is 0.5 and depreciation factor 1.4. Determine the number of fluorescent tube required, their spacing, mounted heighting and total wattage, and total luminous efficiency of fluorescent tube as 40 lumens per watt and 80 watt tubes for 80 watt tubes. So gross lumen requirement is A into E into D, depreciation factor divided by utilization factor, and from there we have calculated this one. Total lumens requirement 151200. And here our room size is 15 meter, hall 30 meters with a height of 5. So we have divided this 50 meter into 10 equal parts of 3 meter, and this 15 meter is again divided into equal 3 meters. Okay, so in that way we have divided this room. Now the total wattage requirement is same formula, total lumen requirement divided by the lumens of 40 lumens, that is 40 here, and for tubes that is 80, so it will be divided by 80. So the number of tubes requirement, that will be total wattage divided by wattage of each tube, that is 48 we are getting. So 50 tubes in 5 rows and each row having 10 tubes and can be used giving 3 meters in length of the well as in the width. These tubes may be mounted at an height of 3 meters and giving space height ratio of unity as per the arrangement shown in the figure. This arrangement will be as per your requirement. You can make your own arrangement as best as possible. Next problem. The front of a building 50 meter into 16 meter is illuminated by 16,000 watt lamps arranged so that the uniform illumination on the surface is obtained. Assuming that the luminous efficiency of 17.4 lumens per watt and a coefficient of utilization of 0.4, determine the illumination on the surface. So the area to be floodlighted, that is 50 into 16, that is 800 meters square, this one. The total lumens given by out of 16 lamps, that is number of lamps into wattage of each lamp into luminous efficiency of each lamp. We have calculated this one, 278,400 lumens. Now the total lumens reaching the surface to be floodlighted, that is total lumens into utilization factor divided by depreciation factor into Westlight factor, and we are getting that 71,400 lumens. Assuming that the depreciation factor is 1.3 and Westlight factor is 1.2, and we are getting the luminous illumination on the surface, that is 71,400 lumens divided by 800, the total flooded area, that is 89.25 lumens, and that is our problem number 6. Previous problem was problem number 5. So we have covered total 6 numericals in this lecture. Now we are just finishing this lecture of illumination engineering. This is the last topic of illumination, and from the next slide, next topics or next lecture, we will start with new module of utilization of electrical power. This total lecture I have taken from the book of J.B. Gupta, Utilization of Electrical Power. You can go through that book. Several numerical problems are there. Practice these problems. Illumination is very important chapter, and illumination is of huge importance for electrical engineer. There is a large domain of lighting which is required to understand by electrical engineers, and that cannot be completed without the knowledge of illumination. So definitely I will tell you that please read this chapter very carefully, and there is a huge working scope in the domain of illumination. So just cover this chapter for your knowledge, for your betterment, and for your working scope in career also. Thank you all for listening my lecture.